Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will learn how to write the mass action expression for heterogeneous and homogeneous equilibria. To begin, we first need to understand what heterogeneous and homogeneous refers to. And so if you recall from the first semester of general chemistry, a substance can explore three different states of matter. A substance can either be solid in phase, liquid in phase, or gas in phase. Now, if that substance just happens to be dissolved in a solvent that's liquid in phase, for example, if the substance is salt and then if the solvent is water, so you have salt water, then that substance is going to be designated as aqueous for its physical state of matter, or its phase of matter. And so overall, the word homogeneous and heterogeneous focuses on the physical states of matter for the reactants and products in any given chemical reaction. And so a homogeneous reaction is when all of the reactants and products have the same physical state of matter. So for instance, if the reactants and products in this general chemical equation are all gas in phase, or they're all aqueous in phase, and the list goes on, then that would be considered a homogeneous reaction. And so a heterogeneous reaction is when you at least have one substance, and it doesn't matter if it's a reactant or a product, but you just have to have one point of difference in terms of physical state of matter for that reaction to be considered heterogeneous. And so what do I mean by that? Let's say, for example, that reactant A, product C, and product D are all gas in phase. Okay. Now, if reactant B happens to be solid in phase, so this is the one point in difference in terms of the physical state of matter, then this reaction would be considered heterogeneous. Okay, so the minimum amount or the minimum requirement is to have just one point of difference. Now, obviously, if you have, two reactant particles or two product particles or combination of reactant and product that are different in phases, then that would also be considered heterogeneous. So overall, what we want to do is we want to learn how the physical state of matter affects the equilibria. And that's going to affect the way that we write our mass action expression. Now, for us to understand how the physical state of matter of a substance affect the equilibria, we need to revisit our mass action expression. And so typically when we write the mass action expression or the equilibrium law to express the equilibrium constant Kc, we're going to take the concentration of the products and raise it to its coefficient. And we're going to divide that by the concentration of the reactants raised to its own coefficient. And so since these brackets represents concentration, we need to understand how concentration or we need to understand how the physical state of matter of that substance affects the concentration. And we're able to better understand that if we look at the units for concentration. And so we know that concentration is typically expressed in molarity units. There are other units that describe concentration, but for now we're going to be focusing on molarity. And so if we expand the definition of molarity, it's molarity is simply a ratio of moles of substances, and moles is a unit of amount, over liters, which is a unit of volume. And so if you guys kind of think about this, if you have a fixed amount of substance, then that value is going to remain constant. And it doesn't really change unless you add more of that same substance. However, volume can change, and it's going to be independent from the amount. And so because we can take 3 pieces of cheese, for instance, or 3 moles of reactant and put it in a 1 liter container, 2 liter container, 3 liter container, etc., the concentration of those substances will change depending on the volume that the substance is in. And if you change the concentration, if you change the molarity, then it also affects the equilibrium constant, Kc. And so to illustrate this effect, we're going to go ahead and I want to draw your attention to this diagram here. And so overall, I want you guys to focus on the dependence on volume for the physical state of matter. And if you guys kind of keep that in the back of your head, then you'll understand why we need to write the mass action expression for specific physical states of matter a little bit differently than others. So let's go ahead and go back to this image. Focusing on this container on the left side of the arrow, here we see that we have 6 particles per given volume. And so just for kicks, I suppose, let's just say that we have 6 moles. So each particle represents 1 mole. And let's just say that the volume right now is 1 liter. And so overall, we get a molarity that's 6 molar. And so if we double the volume of the container and fill it with solvent, and so let's just say that we double the volume, so that way we have 2 liters instead of 1 liter, but we're still going to keep the same number of moles of substance. If you calculate the concentration, so here we have 6 moles, or 6 particles, for every 2 liter. And so if you calculate the concentration, that's going to be 3 molar. And so this concentration is it's highly concentrated. And this concentration has been lowered or diluted. Okay. And so if you guys were to plug in these values for the mass action expression, then the equilibrium constant, the value for the equilibrium constant, is going to change. And so, therefore, the physical states of matter that is dependent on volume, in other words, changes in volume will change the concentration, needs to be taken into consideration when you're writing the mass action expression. So there are 2 physical states of matter that we have to pay close attention to, and that's aqueous and gas phase. And so both of these physical states of matter, gas and aqueous phase, this effect is going to be observed. And so, for instance, instead of saying that this is aqueous, we can say that this is gas in phase. Okay. And so if you were to keep the same number of particles, but you were to increase or decrease the volume, then the concentration or the partial pressure, and we'll talk about partial pressure in another lecture video, the partial pressure is referring to the amount of gas, if you will also change. And so the moral to this story is that we must incorporate substances that are gas or aqueous in phase when writing the mass action expression or the equilibrium law. It's because there's changes in volume. And that's because the concentration will change if the volume change. Okay, so there's a dependence on volume for both aqueous and gas phase. So what if we have something that's solid in phase? And so it turns out that the molar concentration of the solid is constant, regardless of the volume. So it's volume independent. And so how does this affect the mass action expression? And so let's go ahead and take a look at an example. So let's just say that here we have, this container, and this substance is going to be solid in phase. And so let's just say that we fill this solid up to 1 liter. Okay. Now, because this solid does not dissolve, its volume, the volume of the solid, is not dependent on the volume of the container. It's dependent on the volume of itself. Okay. And so if we were to double the volume of the container, and so I'm going to go ahead and take this and duplicate it. And if I were to fill this to the top, for instance, and so this is 2 liters, once again, the solid, since the solid does not dissolve, okay, the volume of the solid is not dependent on the volume of the container, it's dependent on the volume of itself. And so therefore, its molar concentration is the same. Okay. And once again, it's because the solid does not dissolve. And so you guys can think of it as putting like a metal ball in a water bottle and putting that same metal ball again in a tub, right? And so its volume, its molar concentration does not change because that solid doesn't really dissolve. Another way to look at this is that if you double the volume, if you double the amount, okay, so in other words, if I were to take this, if I were to take this solid and double it, notice that the concentration is still the same. Once again, the amount per volume, the ratio between amount and volume, is the same. Okay. And so overall, we do not incorporate substances that are solid in phase and liquid in phase when writing the mass action expression or the equilibrium law. So this is the moral to this story. And so real quick, I did put in liquid in phase and I didn't really explain why, but I'll just go ahead and do it right now. And so what I'm going to do is I'm just going to simply copy this diagram. And then I'm going to paste it over here and I'm going to erase some stuff. And so typically for liquid, you're talking about the concentration of pure solvent. So what I'm doing is I'm erasing all of these particles, these solutes, just so we have pure solvent. And so an example of pure solvent is water. Okay. And so if we have 1 liter of water, the ratio between the amount of water to its volume is going to be proportional if you double the volume, right? If you double the volume for liquid water, for the solvent, the amount also is doubled, and therefore the ratio is going to be the same. And so once again, the molar concentration of liquid, which is typically referring to this solvent in a solution, is constant. And therefore, there is no need for you guys to incorporate that specific substance in your mass action expression. And that's really the main point. And so the last thing that we're going to do for this lecture video is practice writing the mass action expressions for the following reactions. And we can express it for both the equilibrium constant, Kc, or the reaction quotient, Q. So let's go ahead and look at this first example. So notice that we have something that's aqueous in phase, and solid in phase. Now, based on what I just discussed, basically if you have a substance that's solid in phase or liquid in phase, you do not incorporate it in your mass action expression. And so we're going to go ahead and exclude this from our mass action expression. And so when we write the equilibrium constant Kc for this specific reaction, it's still a ratio of products to reactants, but specifically only products and reactants that are aqueous or gas in phase. We ignore liquid and solid completely just because their molar concentration is constant and it will not change or affect the value of the equilibrium constant Kc. And so typically when we write the mass action expression, we're going to write the concentration of AgCl raised to the first power because there's a 1 in front of this chemical equation, or one in front of the chemical formula. And then we're going to divide that by the concentration of Ag plus, and that's going to be multiplied. Let me erase that real quick. Multiplied by the concentration of Cl minus. They're both raised to the first power. However, since this is a solid, then we're going to go ahead and cross this off. And so therefore the mass action expression for either Kc or Q, because remember that we both write them the same way, it's going to be 1 over simply the concentration of Ag plus times that by the concentration of Cl minus. They're both raised to the first power. And so once again, since this substance is solid, doubling the volume or doubling the amount for that solid will not change the value for Kc and Q. So why bother writing it at all? And so we're going to cross that out and we're just going to use 1 as a placeholder. Okay. All right, so looking through the second example, notice here I have something that's aqueous, liquid. Maybe I'll highlight that in a different color. Okay. And we have H3O plus, that's going to be, it's aqueous, so I'll highlight that in yellow. And H2PO4 with a negative charge, I'm going to highlight that in yellow because that's aqueous. And so if I wanted to write the equilibrium constant Kc, or the mass action, or the reaction quotient Q, if I wanted to write the mass action expression for these two, then I would only incorporate substances that are aqueous or gas in state, because any change in volume will affect the equilibrium constant Kc or Q. And so overall, what I get is the concentration of H3O plus raised to the first power, because there's a 1 in front of this, times this by the concentration of H2PO4 with a negative charge, and there's a 1 in front of this, so there's a 1 as an exponent. And finally, I'm just going to write phosphoric acid, the concentration of phosphoric acid in the denominator. And since there's an invisible 1 as the coefficient, that means the exponent is 1. And so hopefully you guys are just catching and understanding the trend. We're just simply crossing out or excluding any substances in the chemical reaction that's solid or liquid in phase. Because once again, they are the value for them is going to be constant if you change the volume. And so doubling the volume, doubling the amount, does not really change the actual concentration. So it doesn't really affect or change the value for Kc or Q. All right, so here we have our last example. I'm going to go ahead and highlight in yellow things that I'm going to incorporate in my mass action expression, which is calcium, phosphate, and in pink I'm going to highlight the substances that I'm going to exclude from my mass action expression. And so here in this case, I'm going to exclude water, calcium phosphate, which is a precipitate. Okay, so a precipitate gets the designation of solid. And once again, I have water. And so very similar to the first example, I can write the equilibrium constant or the reaction quotient. I can write the mass action expression for the equilibrium constant or the reaction quotient as 1 over the concentration of calcium 2 plus raised to the third power, because it has a 3 as its coefficient, times this by the concentration of phosphate raised to the second power, because it has a 2 as its coefficient. And so everything else is excluded, and that's how you guys write the mass action expression for heterogeneous equilibria. All right, so that's it for this lecture video. I'll go ahead and catch you on the next lecture video. Bye.